Good day students. In this video lecture we will be seeing the k nearest neighbor classification algorithm. So let us first go through the high level summary of this classification algorithm. So what does it say means, let k be the number of nearest neighbors and capital D be the set of training examples. So now what we have to do means we have to run through this for loop for computing the distance between the test example and its training examples. So for each test examples z is equal to x prime comma y prime, what we have to do, compute the distance d, that is x prime comma x, that is between the test example and the training example, the distance between z and every training example x comma y, that is belonging to capital D. Once this computation is finished, next we are going to select the dz, which is the subset of D, the set of k closest training examples to z. Then at the end what we are going to do means we are going to classify the test example according to this majority voting scheme. What does it say? Y prime is equal to arg max of summation of xi comma yi belonging to this dz, that is the subset of D, then this indicator function I. So here this small v is a class label and yi is the class label for one of the nearest neighbors. So v is the class label and yi is the class label for one of the nearest neighbors, and I of this is an indicator function that returns the value 1 if its argument is true and 0 otherwise. So once the nearest neighbor list is obtained, the test example is classified based on the majority class of its nearest neighbors. So based on the majority class of the nearest neighbors, we are going to classify according to this particular formula, that is based on this indicator function. So please remember here that whatever the indicator function we have used, it is going to work on the discrete target values or the discrete labels. So if it is continuous values, then we have to go for the continuous valued matching function over here. But here we are going to take whether the class label matches or not. If majority of them are matching, then we return that value as 1, otherwise 0. Now in this particular case, what is going to happen means, impact of all these k nearest neighbors or k closest training examples are same. One example may be a bit far away from the particular test example, one may be very close to it, but all of them are having the same impact. So in order to vary the impact based on the distance, what we are going to do means we are going to introduce a distance weighted voting, where we are going to weight our distance. So what is this weight? Weight is actually the inverse of its distance from the test example. So it will be, that weight will be wi is equal to 1 by d of x prime comma xi, that is between the test example and the training example. Inverse of its distance will be the weight, that will be multiplied with this, so that impact will be based on the distance from the test example. So this is what is going to happen in the k nearest neighbor algorithm. Next we will be seeing briefly about the characteristics of the nearest neighbor classifiers. So as we have seen earlier, the nearest neighbor classifier does not create any explicit model, so it is a part of more general technique known as the instance based learning. So what it does means, when a specific instance is given for the classification, it will try to match with the similar instance in the training examples. So how this distance is measured? So there are various functions. I could have told that in the algorithm, this distance d is computed according to a particular distance measure, which we have already seen in the module 2. It may be the Euclidean distance, it may be the Manhattan distance, or Minkowski's distance. It depends upon which distance function you are going to take. So in the d-dimensional space, these uh, X training examples are being represented, or capital D set of training examples are being represented, where we represent the feature set with the X and Y is the class label. So this D is the distance. So nearest neighbor classification is a part of more general technique known as the instance based learning. That is the one characteristics of that. And lazy learners such as nearest neighbor classifiers do not require the model building. Again, we are repeating the same point. It doesn't require any prior model building based on certain mathematical functions. Classifying a test example can be quite expensive here, because we need to compute the proximity values individually between the test and training examples. Suppose if you are having a very big number of training examples with very high dimensionality, then computing the proximity may be very expensive. So in contrast, eager learners often spend the bulk of their computing resources for the model building itself. Once a model has been built, classifying a test example is extremely fast, which doesn't happen in case of the nearest neighbor classifiers. Then we are having the nearest neighbor classifiers make their predictions based on the local information, that is the how many training examples are near to that. Based on that, classification is being done, whereas in the eager learners like a decision tree and rule based classifier, they attempt to find a global model that fits the entire input space. Then nearest neighbor classifiers can produce the arbitrarily shaped decision boundaries. Uh, Such boundaries provide a more flexible model representation compared to the decision tree and rule based classifier, which are often constrained to the rectilinear decision boundaries. So if the decision boundaries are very constrained, then it is very hard to classify the training examples with the uh, different decision boundaries. So nearest neighbor classifiers are comparatively easier since they produce the arbitrarily shaped decision boundaries. The nearest neighbor classifiers can produce wrong predictions unless the appropriate proximity measure and data pre-processing steps are taken. If we are not properly engaging a particular proper proximity measure, then there are high chances that we may go wrong and end up in the wrong classification. So that should be taken into account, uh, and much needed measure is to be computed. So this brings us to an end of the nearest neighbor classifiers lecture. Thank you.